Good afternoon, guys.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Okay, thank you. Dungog di ay. Okay, we will start. Okay, medyo lisod-lisod na ato ang ano part. Okay, we begin with a prayer in the name of the Father, of the Son, of the Holy Spirit. Amen. Heavenly Father, and your beloved Son, Jesus Christ, we thank you for giving us another life. We thank you for another beautiful afternoon. As we go on through our lessons today, may you make us instruments to do good things. Please enlighten our minds. Give us the strength to participate in our subject today. Thank you for this opportunity to learn and serve others, and help us to always remember the truth of your glory. In Jesus' name, amen. Again, good afternoon, guys. Or good evening, no? Okay, we'll have our attendance first. Maklaro ba ninyo ang kuan? Na project ba?
Yes, sir.
Okay, Abarkes,
Present, sir.
Abrasaldo,
Present, sir.
Anchita,
Present, sir.
Arong, Arong wala.
Present, sir.
Okay, okay. Barrios, Kevin,
Present, sir.
Belvestre, Gitchel,
Present, sir.
Kanyete, Kanyete Hana,
Sir, wala day signal ilang kakanyete, sir.
wala siya di siya ka-attend karon, no?
Dili daw, sir. Yes, sir. Kaya walay signal or what batoy kurente. Nakamalihog ra siya ganiha, sir.
Caballero, Caballero Saidel, wala. Castañares, Shime,
Present, sir.
Clemente,
Present, sir.
Cuyos,
Present, sir.
Dakay,
Present, sir.
Iglasa,
Present, sir.
Upol,
Present, sir.
Durham,
Present, sir.
Scario Jan,
Present, sir.
Fabrique,
Present, sir.
Figueroa,
Present, sir.
Giliena,
Present, sir.
Jarina,
Present, sir.
Groma,
Present siya, sir, pero wala daw siya yung mic. Pero atin siya sa meeting room, sir.
okay. Leopando,
Present, sir.
Luwab,
Present, sir.
Lumibaw,
Present, sir.
Yuli,
Present, sir.
Purok,
Present, sir.
ah,
Present, sir.
Alice,
Hi, sir. Present.
ay, Pipito,
Present, sir.
Perez, Perez,
Present, sir.
okay.
Present, sir, Perez.
Randas,
Present, sir.
Ponte,
Present, sir.
Robin,
Present, sir.
Sanoy,
Present, sir, Sanay.
Ilio,
Present, Sir Sinilio.
Suson,
Present, sir. Susan.
Toledo,
Present, sir.
Vergara,
Present, sir.
Yaon.
Present, sir.
Okay, so atong absent, Kanyete o Caballero. Okay? Okay, we'll start to our topic. Actually, atong topic karon is diretso na ta sa mole balance, no? But then I realized nga if we are going to do these things, direkta ta sa to ang chemical engineering balancing like the reaction rate. Murag maglisod siguro ta og kuan dai, no? Especially these things ano kining general mole balance, no? Kini anin din nga to ang kuan. So I believe before ta nimo siguro ugma na ni siya or sa Monday na or sa Tuesday na to ni this is the heart, no? Mao ni ang pinakabuod sa ato ang kuan. And this is very long topic, no? Everything needs your prior knowledge, no? Tanang knowledge ninyo kinahanglan ma-apply na diha regarding the chemical, no, engineering. Okay, so what I'm going to do is to give you the theory, no? Murag mag-recall ta sa atong mga theory regarding the mole balance, no? In relation to this subject, no? Chemical reaction engineering and kinetics, no? Ato lang ipang recall. So, ito ning Moderikta tangad to sa ato ang video. Wait. Not this one. Okay.
What's up, guys? It's me, chemical engineering guy, and we're going to continue with the topic
So this is a
of
video taken
mass
from the
balance
YouTube
course, which
by
is
the
the
chemical engineering guy,
introduction,
you know. Pwede rin nyo
MB
makita
number
ningat to
one.
sa kuan YouTube.
We've seen MB number 0, which is essentially just like the overview of the course. Sorry about it. And yeah, let's continue with the next chapter, which is essentially only 2 sections. The content here is section 1, which is the theory, which I like to call the basics of process or chemical engineering. Like the the least stuff you need to know, at least as a chemical engineer, is here. We're going to see a lot of stuff like this: system, process, unit operation. This one is very famous. We're going Actually, there are courses based on this one: streams, flows, variables, flow diagrams. This one is also very important. And finally, theory or mass balance. Now, that was only theory. We just need to learn it. Section 2 is the most important part, because one thing is to know, another thing is to do. We're going to do, well, first learn some mass balance basics, like theory, how to understand the mass balance, where to start, where addition, production, consumption, accumulation in the system, all these things, we're going to watch them here. Now, once we understand the basics of mass balance theory, we're going to see some problems and exercise. These ones are the ones that are going to help you to understand. Now, let's continue with section 1. It's some basic theory in engineering and process engineering. As I told you before, it's very easy because it's just to learn. It's very important to understand it. Don't just learn it by heart, but at least learn it very hard if you cannot like remember, but understand. You need to understand what is. When I say a system, you need to understand what is a system, what is within, what is without, etc. Now, let's continue with the theory. The basic definitions that we're going to see are these ones here. Now, like chemical processes are in general processes that involve some stuff of chemical, like production, reactions, etc., products, reactants, blah, blah, blah. We're going to see what is a unit operation, how to distinguish from other like non-unit operation things. Then streams, flows, is essentially all the arrows you see in a process. It's, I don't know, matter being held here, matter. Then process variables, which is like pressure in the tank, temperature of the current or flow, composition of A in the flow, velocity, height of the tank, etc. Now we're going to see what is a flow diagram. This is very important because we are going to base our problems in this one. And actually we have three, which we're going to see furthermore. Then, well, this one should be inside of this flow diagram, block diagram, etc. Then we're going to see this here system. Probably you've seen or heard me before telling you system, system, system. We're going to analyze these three systems: open system, closed system, and isolated system. Actually, the most important one is this one. I will say like almost 90% of the course is here. Closed system will be the other 10%. And since isolated system imply energy, we are not going to see this in this course. You may consider an isolated system as a closed system. And finally, we're going to see some things about mass balance. Now, let's continue. I told you we're going to see process. Let's give a formal definition of process. Process is simply a series of actions or steps taken in order, it's important, in order to achieve a particular end or product. You may see, I don't know, you start here, you go here, then you go here, you finish here, etc. I'd like you to present you better a diagram of crushing plant. Crushing plant is nothing but this process here. And one thing that I want to show you is that actually processes are made many times out of many processes. All these circles are processes, and the total of these processes makes another process. But okay, let's see. Number one is you need to bring the you need to bring the stones from the mine. Number two, you need to put them or throw them in this van to transport it. Number three, you're going to crush them. But it's not like that fine, okay? We continue, we go to the impact crusher, keeps crushing and crushing. Then we bring them here. It's already crushed. Then we're going to vibrate, and they will go very, very finely crushed. You see, this is small, this is medium, and this is big. Now you see each process transporting, crushing, separating, and storage. All these processes make a whole process, which is called the crushing plant. So just take importance that you can always make sub-processes inside a process. Now, let's understand the difference between a normal process and a chemical process. A chemical process is essentially, let me show you the meaning of Wikipedia. I like it very much. It's a chemical process is a method or a means of somehow changing, you need to have a change. One or more chemicals must be involved, or chemical compounds. It can occur by itself, it's not that normal, or caused by an outside force, which we are going to give. And it always involves a chemical reaction. If there's no chemical reaction, it is not a chemical process. Okay? So just learn this change of chemicals, outside force, and it involves a reaction. If you understand that, you are going good. Now, this is a chemical process. The production of mighty beer. I love beer. You love this, you've probably seen one before. It consists essentially in milding, mashing, lautering. This one is very important, boiling. Then comes the whirlpool. Then comes the cooling. And the most important part is the fermentation. This here that I'm making this circle here, it's the one that has the most important chemical reaction. So this one here makes the whole process a chemical process. But for example, milling is not that chemical process. Mashing probably not, it's only mixing water. It may have some chemical reactions, but it's not the main chemical reaction. The main chemical reaction comes here. And also maturing, but not that much. Filtering is only taking stuff out of the liquid, and packaging does not evolve generally. Then it goes to distribution. So this process, this whole process, it's a chemical process just because there's a fermentation here, a chemical process. Okay. Now let's keep going with the type of diagram. The block diagram, maybe you know it is the most simple one. Flow diagram is a little bit more technical. Let's say if it's a tank, you might add here something more, like you will say only tank here. You say tank here also. Maybe you add extra data, temperature, pressure, steel, materials, etc. And this one here is like the most complete one. It will actually tell you like, oh, you have this like electronic device here, and this one goes here. This pipe is about 4 inches. I don't know, it will be more complete. I'm going to explain them in the next slides. Now, block diagram, easy. It's a simple diagram that shows at a glance the process. So no complications. I just want to see here the reactor. There's a gas separator and a distillation. It's the most used for mass balance solving. Why? Because we don't need to know how the reactor is operating. We just need to know the mass balance, what enters and what goes out. Now, gas separator, you don't need to know the mass separation principle that it works. You just need to know how much concentration or flow is going here, the mixed liquids, the concentrations, etc. And the distillation, you don't need to know how it operates. You don't need to know how many plates do you need, how much must be the diameter of the tower. No, you just need to know what goes up, what goes down, or the feed. Okay, so this is the most used because it's fast. Just if you're just interested in the mass balance, you just keep doing these ones and ignore all the ones I just draw here. Now, it's very important to include flows. This is the ones you need to include. These are all these arrows. Unit operations. I told you you don't need to know how they operate, but just like show them so you know, like this box makes something magical. I like to call this like this black box because you don't know what happens there, but something is happening. That's put it there. And some extra data, for example, conversion. Actually, you don't know how this, you don't know how does it works, like how many degrees or how much energy it needs. You don't know like the reactions or etc. You just know that there's a 75% conversion. Okay, basic. Now let's go for the flow diagram, which is essentially the same, just with a little bit more data. For example, you have this here, you divide it top, bottom, you show the heat exchanger, a pump maybe, a storage center here, your main operation unit, you show this valve, etc. This is like the typical process flow. Not that much information, it's enough. I don't recommend that much to do this like in mass balance, because then you will need like this current then mixes and comes to this valve. Let me do a mass balance in this valve. Doesn't make sense because it's actually just entering the same and the outlet is also the same. Also in a condenser, the only thing you change is temperature, maybe a little bit pressure, I don't think so. So just keep with the temperature. So entering here, the stuff entering here, the same as the outlet, so ignore that, okay? But it's important if you actually are doing like a mass balance and energy balance, you will have to have where is the condenser, where is the heat exchanger, where is this one here, the boiler, etc. Now, this one here, probably you've seen it before, maybe not, is the most typical diagram or formal diagram you will see, the pipe and instrumentation diagram, which is pay and ID, or I say just PIP. It's formal language. You can actually look just in internet, pay ID. You will find a lot of data, like PDF or even manuals talking about what do you need. Like if you have this valve, I don't know, it's a special valve, you will have to draw it like in a special manner, something like that. And this valve here is another one. And this valve here will be other, etc. For example, you see, as I told you before, you can see the type of valves. They show you which type of valve. Not only there's a valve, but which type of valve. You can see the piping information. This is very important, because actually knowing the size of pipes helps you to know velocity, to know the diameter, to know maybe the friction factor being lost in here, etc. You can see more detail in the operation unit. Maybe, I don't know, if this is a boiler, I don't know, you may see how many tubes it needs to operate. Or if you see a distillation column, you may see how many dishes does the distillation column has. And finally, but not least, automation units or equipment. These one here are very important for safety and for control. So imagine you have a variable that is changing. You need to open and close and open and close. So if a human will do that, it will be like not that convenient. You need something automatic that controls that. And also for safety, you cannot like just tell a guy to sit here and tell them like, hey, can you watch so the tank here doesn't spill out. Like, will be wiser if you, I don't know, just buy a laser automatic sensor here, and well, you got the idea. You have this one here. Now let's continue. I absolutely do not recommend this for a mass balance. Actually, if you're working and you have this, you will probably do like, okay, all this part or all this can be called like a black one, and you don't need to take care. And then you will see actually this one is one. All this one here, let's say it's like refrigeration unit. Put this refrigeration unit, and you put all these, and you say, I don't know, this is like the vapor recuperation unit, etc. You can do systems over this system, so don't worry. And finally, let's talk about some unit operations. It's a basic process step in a chemical engineering process. The unit operation involves almost always physical change or chemical transformation. If you don't have none of these, you are not having a unit operation. So always remember physical or chemical change. Example, separation is physical, crystallization is physical, evaporation is physical, filtration is physical, polymerization is chemical, isomerization is chemical, and other reactions, obviously it's chemical from MIT Wikipedia. Now, let's see some unit operations. I put them here in red. You can see the ones about reactor engineering, which is actually just a reactor. Anything that reacts, you can call a reactor, so that's why. Now let's see the heat operation units. What do you can use for heat transfer? You can either condense, evaporate, or simply exchange heat. This is more like to increase or decrease temperature. This is to change liquid to gas, and this one is to change gas to liquid. You could also have a freezer, etc. Now let's continue with the mass operations, which is the most large section here. And we have crystallizer, filter, cyclone, any separator, any mixer, a distillation column, absorption, which is not the same as adsorption. Okay, just remember that. Apps and app is a totally different stuff, so take care. And finally, we see some unit operation of momentum, which are in general pumps, compressors, and maybe a storage tank. So just keep those in mind, and you will get the idea of what unit operation we are talking about. In mass balance, we're going to see a lot of unit operations, so don't worry, just if you have doubt, just check what the unit operation is. Like if I tell you it's a dryer and you don't know what's a dryer or how does a dryer operate, just check. Have an example. How do you see this in, I don't know, in the school, in the books? Very nice. You can see actually everything. And the problem is when you get to the real life, you don't see that much. You only see outside, some tubes here, maybe inlets, but you don't know like where all this here and here is the same here. You'll see the column for head and bottom. And you will see also here in real life, you will see a lot, but here you don't see that much. But there are many stuff here. Actually, there's some escalators for men. Heat exchange. Oh, sorry, last one was distillation column, which is mass transfer. Heat exchange will be simply a tube heat exchanger, which is many tubes go here. You will see that in mass and in heat transfer class. You will see it. But the idea is that it goes fluid like this, and the other fluid goes through the tubes. They don't touch physically. One goes inside the tube, and the other one goes outside the tube. So they are touching each other here. The real life, well, this one is very nice. You can actually see the tubes, but the real one life, you will see only like this huge pipe. You will see like I thought it was a pipe, not a heat exchanger. And a centrifugal pump, which is the momentum one. Okay. Diagram picture, you will see simply this, or even something like this. But in real life, you will see like there's a motor here, and there's the inlet, then it goes out. Let's continue now with the process variables. The process variable is, in general, a process value here, or a process parameter, which shows the current status of a process under control. Examples are various temperature of a furnace. You have this, you're burning, and you want to have a temperature, I don't know, 1000 Celsius degrees. And that's what do you want. But actually, let's say you're only getting 950. This is your process variable. And this is your set point. And the most logical thing to do will be to burn more fuel to increase temperature. So you're going to try to get this process variable to be the same as the set point. Typical process variables are pressure, volume, temperature, density, height, concentration, flow, and also conversion. I will recommend you guys, if you can do it, get to know how these process variables are measured in real life. So pressure, you only, like you will see a lot of computer stuff, but there's actual eventually something that connects, I don't know, for example, there's a spring and you know the spring and you know that it is here, it's 50 psi, and it shreds, it shrinks here, then it is 200 psi, okay? Makes sense. Temperature, well, you know it, maybe simpler with this thermometer, density, etc. Now let's continue with the flow. What is a flow? We're going to talk a lot of flows. So please understand this. We're going to talk about mass flow, mole flow or molar flow, and volume flow or volumetric flow. So a mass flow, in general, I wrote down here the international units, which is kilogram per second, is simply mass flowing per unit time. How much mass I'm transferring per unit time. Now, the molar flow, it's essentially the same, but not mass, it's moles. How many moles I'm transferring per time. And finally, volumetric flow, it's typically cubic meter per second. It's how much volume I'm transferring per time. So hopefully you get that. If you don't understand this, it's simply like if you have one glass of water, you are getting water inside here, here. How much time do you need? How much volume is it? Then you will see that you can calculate the volumetric flow just like volume in time. And you can play with this equation, like how much time will I need to fill the volume here if the volumetric flow is this one. So it's really, really easy, guys. Don't worry, we're going to use them later in exercise. This is like the general, like how much quantity of mass, mole, volume is flowing per unit time. And I have here some examples, like what is normal to see, like 10 kilograms per minute, 1 pound per second, 350 kilotons per year. I don't know, maybe this is a plant production. 3 milligrams per day, I don't know. This is maybe how much calcium you need per day, I don't know. Mole flow examples. 1 mole of water per minute is actually not that much. 3.02 kilomole per hour. Depends on the substance. Maybe if the molecular weight is big, it will be a lot of mass. So if this is a polymer, it will be a lot. And 125 pounds per second. You know, well, pound mole. We're going to see that later. Volume flow examples, those one are easy. I already explained that. This one, 1 liter per minute. That I think is the most like intuitive one. 1 liter, you know, it's like a tetra pack of milk per minute. Imagine if I told you this cow has 1 liter of milk per minute, right? So you could in 60 minutes fill 60 bottles of 1 liter. 4.5 milliliters per day. I don't know, maybe this is medicine. The medicine you need to take. And 18,000 gallon per year. Maybe acid rain in a city or in a pound. I don't know. You be creative. This is where we're going to put our flow examples. So we have the arrow and we generally try to put them in the arrow so we know fast, very fast, where is it. Look here and here. These one are the operation units we already saw. And it's time to enter this last part, which is the state of the system or the system state. What do we mean by state? We're going to see this. Steady state is typical for continuous processes, and transient state is also known as unsteady state or non-steady state. Makes sense? Like the counterpart, steady versus non-steady. And typical for batch and semi-batch processes. We're going to see these ones later. So, steady state, when all values of all variables in a process do not change. That I remark not and time. So imagine this diagram. You have this diagram. The operation of a plant typically is all year, 24 hours. So what you will expect is I have this reactor. I want it to work at least 10 years with this flow. I want to keep this flow. Suppose that we don't have an increase in demand. That will be nice. Actually, in real life, you do have a decrease or increase of demand. So you only need to take this amount of benzene. You're selling almost 8.2 ton of benzene. That is what you're selling. I don't know, maybe you sell it, no idea, $10 a kilo, which I think is a lot. So if you keep working like this, you want to, well, if you have 2 tons of toluene, you need 820 kilograms of hydrate. So keep doing this. You will have this conversion always the same because it's operating continuously. The gas separator will always separate this amount of gas with the concentration of A, B, and C, blah, 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 the same, and our product will be the same purity here. So after 1 year, the concentrations, flows, and other variables will be or should be the same. Now, what happens when that does not actually happen? Let's see it here. The transient state is essentially when any of the variables changes with time. So there is actual change. Now I brought here, let's see, we have a pot. And we are here with fire. And in the example, I don't know, you have 10 liters here. I don't know, maybe it's water. And in time 0, you have those 10 kilo or 10 liter. Let's say 10 liter, which is, if it were water, it would be 10 kilograms of water. After 5 hours, time 2, that will be 5 hours later, you only have 2 liters, which is about 2 kilograms. So of course you lower the level, you lower the mass inside. If you are making the balance here, you increase here, you decrease here because it goes here, 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 evaporates, condensates, and comes here. So transient state, just be thinking about there's a change in time. We're not going to see that much. We're actually seeing like 10% of these. The course is based on this transient state. The most typical one is the continuous one, so pay attention in that one. We have other types of classification, which will be the batch process. This is a process that is being fed once, then time elapses, and then the process products are removed. So you feed, you close, you react, and you discharge. Continuous process, as I told you, it's the input and output flows react continuously throughout the duration of the process, so there's no change in time. The semi-batch process will be the combination of batch continuous. So you have some type of this process batch, and you have this type of continuous process. For example, charging a reactor. In general, when you are like starting up a reactor, you don't have the desired concentration. So the first 5 hours, the concentration of A, let's say, starts at 0 and finishes in, I don't know, 20%. And then you can operate the reactor at 20% all what you want, all time long. But you need to change from this 0% to this 0 to 20% here. So just pay attention. We're not going to see this too much. This is more like typical in reactor engineering, but you need to at least know that it's a semi-batch process. And the type of system we're going to see, system, remember we already saw it. Open system is there is inlet, something enters, there is an outlet, something goes out, and of materials I'm talking about to this system. So we have inlet and outlet. Closed system, as the name says, it's closed, no inlet, nothing enters, and no outlet, nothing goes out. So it will be like this materials. And the isolated system is no inlet, okay, no inlet, no outlet of materials, but we need to include also that there's no inlet or outlet to the system. So here we can actually interact with heat, and here we cannot interact with heat. So this is like the most perfect case, which actually does not exist, but we can approximate many systems to this. Actually, I have in the next slide, I have these examples here. Open system will be this. The bubbles go out, dust can come here, and what else? I don't know, maybe even a bug, etc. Water can also evaporate, so there's inlet and outlet. It's an open system. A closed system, by the other hand, nothing can go in and nothing can go out. But you know that if you let this in your, I don't know, office, it's, I don't know, it's 5 Celsius degrees, super cold. You like it that way. And then, you know, we are 30 degrees ambient temperature. So the weather will eventually go up and this bottle will be the same temperature as the air. There's heat exchange, okay? And finally, the isolated, which that's why I'm telling you that technically it does not exist. It will be this one here. You have no inlet, you have no outlet. Besides, there's like, because this material is so non, it does not change energy. It's like super bad conductor. You can suppose, like, I don't know, maybe the first 15 minutes the water will be like those 5 degrees, whereas here it will be, I don't know, it's already 10 degrees in 5 minutes. If you let 5 minutes, it increases here, but 5 minutes here it does not actually move. So you can say that in 15 minutes you can treat this system as isolated. So just keep in mind these ones, guys. Open is the most common, enter, out, inlet, outlet. Close it is okay, more typical in thermodynamics. And isolated is ideal, actually it does not exist, but we try to be like that. So don't worry, just reread if you do not understand the example. I think it's clear. Inlets, outlets, energy involved, etc. And the last thing I'm going to watch is this one, the type of systems according to variables. What happens when the pressure is constant? It's isobaric. What happens when the temperature is constant is isothermal. What happens when the volume is constant? Isochoric, which is not that common. Like the name, I mean, have you ever heard before isochoric? I didn't hear it before, so I think it's kind of exotic. And adiabatic system when there's no heat exchange, like an isolation. And that was everything in this section 1 of this chapter, mass balance theory. Please make sure you understood all the material before advancing to the next section. And I'm talking serious, guys, because if you do not understand what's a process, what do I mean with open process, open system, and process variable, etc., you will get lost in the next section. So please, guys, make sure and enjoy your course. Welcome again to the course of mass balance. In this video, we're going to take some theory about the mass balancing, which is in general, what is the mass balance principle? It's easy, don't worry. Is, and actually I'm pretty sure you already know it, is that mass or matter can neither be created nor destroyed. So that's good because then we know that matter will always be the same because it doesn't destroy, disappears, creates. The only thing we're going to see is that it's being transformed. So because we're going to see some chemical processes, we're going to account that transforming as production of a species, production of I, and consumption of a species I. So just that. That's cool, I think, because you can do an actual equation like add inlet minus outlet equals accumulation, or I don't know. If we didn't have this, we could not do the equation and it will be probably a guess. So that's cool. It's cool. We're not going to see energy in this course, not at all. Actually, many students tell me like energy and mass, they have a relationship. It's equal, actually this one. It's very famous. Here's energy, here's mass, and this is the speed of light to the second power. No, we're not going to use this because this is only in nuclear reactions. It's true, nuclear reaction is a chemical reaction, but we are not going to see these reactions in this type of process. We're going to see only chemical conversions that don't involve like nuclear chemistry. So don't worry. You want to learn more about energy, you can go to the energy balance course. But in this course, we are only concerned in mass. Got volume. Yeah, just go to the energy balance course if you really want to learn more about energy. And okay, what's the principle in general? Remember, the definition of a system is any portion of the universe. You choose it, but if you choose it, you need to delimit with boundaries. So let's say in this case, I have this system. Inside, it could happen a reaction. We could be mixing. We could be splitting. We could be drying. We could be humidifying. I don't know, like many things. We could be heating. We could be pressurizing. I don't know. There's many processes that could happen to the system. And of course, if we are talking about mass or matter, you could like get inside matter. For example, if you have a house, you could go inside, bring groceries, you're bringing food inside the house. And of course, you can have also outlets. If you, I don't know, take all your garbage out of the house, you're taking out matter. You go inside, goes food, outside goes garbage. And consumption will be, I don't know, if you are eating food and then, well, technically I don't want to explain that much, but there's going to be a consumption, there's going to be a production. I'm going to make an example later, further on, so you can get the actual knowledge of what is this consumption and what is this production concept. But in general, just get to use get used to inlet, outlet, consumption, and production. And of course, the system. So the mass balance analysis is going to be this red square. Make sure you get all the streams or all the flows with the square or your system, because if you do something like this, you only get this outlet, this inlet, this, you don't get it, and you get this outlet, you will be asking yourself, oh, why I am, I don't know, accumulating, why I'm getting, I don't know, if it's air, And this is very typical in engineering. You probably think it's pretty dumb, but actually you sometimes don't actually know if you are getting another stream or something is entering the oven. For example, you have a furnace, you have fire in it, and you are asking yourself, oh, why I need to burn that much if it's not that much matter? And you will get to use that there's a small stream of, I don't know, air or even water. Like water is dropping and it's cooling the wall, and that's why you need more energy and therefore you need more fuel. So it's very important to get to know the system and actually do the boundaries and get them well. Once you have the boundaries of your system well selected with all the streams going in, all the streams going out, you can worry about consumption and production. So, as I said before, this is the system. Now we want to do an actual equation. So if I wanted to know matter or how much mass is going inside the system, for example, if I have this glass of water is empty and I start filling it, I'm accumulating water. Or for the other side, if I have, I don't know, this big container and I'm have it full and I'm actually emptying it. And this is my system, this is my system. Well, the concept of accumulation is how much matter per time or unit time are you accumulating or I don't know, like not accumulating. So this will be done with these four concepts: inlet, outlet, production, and consumption. The inlet is here, as I told you, and we could have many inlets anywhere. It doesn't have to be right or down. You could have many outlets, actually an arrow just going out of the system. Also, you could have it everywhere. The concept of production, if you're having a chemical reaction, you are producing, I don't know, you have a reaction A reacts to B with a lot of temperature, then you're producing B. You are asking yourself, oh, why I'm increasing the concentration of B? It's obvious because you're actually converting A to B. Now consumption will be, for example, if you're doing a mass balance in A on A, you'll be asking yourself why A is disappearing, because of course it's reacting to convert to B. So either consumption and production. Hopefully you get to use those concepts and understand them. And finally, because inlets go plus, we're getting more matter. Outlet is taking out matter. Production, of course, is getting more matter. These ones are specials. I'm talking about chemical reaction. Minus consumption. This will accumulate in your system. And this is very tricky because I know you probably are asking, I just told you before that there's no production, consumption, that we don't destroy nor create matter, but I'm talking about chemical species. If I do this mass balance, actually a normal mass balance, like kilograms, you will never have this. You will never have production nor consumption. But if we're talking about moles of A, mole is a molecule, you will have an inlet, yes, you're feeding, and you have an outlet that probably, I don't know, reacts. It doesn't react that much. In this reaction, doesn't react that much, so you have an outlet. You have a production? No, you don't have production because it is converting all to B. So we have consumption here. So just get a little bit this is kind of tricky. Production, consumption, just know that we're talking about chemical reactions. So of course there's going to disappear A, but it's in mass. A is actually converting to B. So 10 kilos of A will never give you 15 kilos of B or 5 kilos of B. 10 kilos of A will give you always 10 kilos of B. That's the mass balance concept. But of course, in moles, you will be like, okay, 10 moles of A are reacting to form 10 moles of B, and I disappear 10 moles of A, of course. So don't get that worried. We're going to see a lot of examples, but just get to know the production and consumption are only in chemical reactions. And now let's do a simple example. I call this the city example. Inlet of people is going in, it's immigration. It will be always positive. Okay, imagine we have this city, it's so cool that many people wants to go in. We're going, 50 people are going in. I don't know, this could be per year. Actually, could be also per day. You know, you're in a cool city, 50 persons per day sounds like normal. And outlet. We're taking out people. People actually don't like the city. They thought it was cool, but they stay there and they say, nah, I actually don't like this. So we're going to have also emigration, -3. And then, of course, inside, we will have inside the city people that is burning. Burning, people is being born. We have these 100 babies per year or per day. It doesn't depend on the size. And of course, you will have people dying. That's sad, but we have these people which are dying or consuming themselves. The accumulation, now hopefully you get to understand what's accumulation. What will be the accumulation of the city? And this is almost intuitive. You will say how much people is, or the growth of the city, how much is it? Well, you just need to do this addition. Will be 50 minus 3 plus 100 minus 25, which I have here. And the number gives you 122. What does that mean? This means since it is positive, you are accumulating 122 persons per year, let's say per year. What will happen if, I don't know, it's not that cool. We don't have that much babies burning and we have no immigration. Actually, it's a shitty city. We only have immigration and people is dying. We will have 0 minus 3 plus 0 minus 25, which will give you minus 28. And what does that mean? Why do we have a negative number? It means that the city is losing in general population. So 28 persons per year are disappearing. So hopefully you get the example because we're going to go to a similar example, but now with more chemistry. So if I ask you what is the accumulation in the system, and I tell you I have inlet of A moles, or no, A kilos of A, it's 100, and I have a production of 0, I'm not producing A. Let's say probably is the reaction I told you before. A is converting to B, so I have no production. And then the consumption is 50. I'm telling that these 50, I just got 100 kilos, and from these 100 kilos, you are producing, you are producing 50 kilos of B, which means 50 kilos of A are consuming. The outlet, well, let's say it's 25 kilos. So it's very easy. I'm putting 100 kilos inside. The outlet is 25 kilos. So in this system, we either have 75 left. 50 are being consumed. So 50 out. So the only accumulation, so the system is accumulating 25 moles. What does that mean? It probably, with time, it will get full of A because it's not reacting, and we will have to take out those moles. So just mathematically, I show you this. The mass balance in the system is 100 minus or plus the production, which we don't have, minus 50, which is the consumption, minus 25, the outlet. Do the math and you get 25 kilograms are being accumulated in the system. So it's easy. You compare it with the seed example, the reactor example is similar. Just get to know what's the inlet, what's the production, what's the consumption, and what's the outlet. That's the actual problem. To know each and to do the math, because this is a very easy example. We're going to see more like complicated problems, so just keep reading. Now we're going to see the mass balance equation. I told you before it was something about inlet minus outlet plus production and consumption. This is very typical for chemical process, chemical reaction. But this is typical for mass balance in general. Is equal to the accumulation. And accumulation, it's always generally mass over time. So mass is accumulating in time in the system. So we do actually account how much mass is getting in this time. And what I want to show you here is that we can do it in, well, we can do a mass balance on a species. When I say species, let's say I could be any value, could be, I don't know, CO2, could be moles of A, or actually just A, could be water, etc. So we could have inlet of water, or I, outlet of I, which is, I would choose water in this case. Production of water, if you are having a reaction that produces water, minus consumption of water. I don't know, maybe you have another reaction that has consumption. This will give you the water in the system, like how much water is being accumulated in the system. So just get used to that. We're going to see that much further in chemical reactions, but just know that we can do mass balance over species. And now we're going to see two different types of mass balance, differential and integral mass balances. Differential mass balance is essentially an analysis in one instant of time, which means one instant means as time goes to zero. We're going to use a lot of velocities or rates, for example, grams per second, kilograms per hour, barrel per day. And it's a typical like process for continuous processes. So since we are very interested in these processes, this typical chemical engineering, you have plants and they work like 24 hours per year, every day. So this is a continuous process. The temperature, kilos, everything, we try to have it the same. So this is a continuous process, if you remember. And the tip I use here is very convenient to use a time base. So I don't know, you say 10 kilogram per hour. I would say like use 1 hour, so you have only 10 kilos to analyze. You don't have to, but I do recommend it. We will use this a lot in the course. This is like 80 to 90% of the balances we're going to use. So please get to know it very, very well. Remember instant, remember it's a velocity or a rate, and it's typical for continuous processes. Now the integral one, which we're going to see only about like 10 to 20%. You're probably asking me why we're going to see this. I don't know. It's very important to do other types of balances that doesn't imply continuous processes. Actually, it's very cool because you are going to do processes in 2 instances of time. So you have time 0 or time 1, and you have final time. So for example, if you are this typical, you will tell me like, oh, why are we studying this? Maybe you're filling a tank. You have, I don't know, 10 liters per hour, and you have 100 liters capacity. You will the I don't know how to explain it. Like, what will be the time needed to fill the tank? And of course, like, with not math, you can say 10 hours. You need 10 hours to fill 100 liter if you're flowing 10 liter per hour water here. You flow here. So that's why we use 2 times or 2 instants of time. We use quantities rather than velocities. I told you before it was velocities, but in this one we're going to use more quantities. As I told you, 10, like how much? 100 liters. I want 100 liters is punctual. Before you wanted the velocity, like what is the rate? Like 100 kilograms per second. But no, now we're going to be more interested in the quantities, like kilogram, ton, pound, liter, etc. The time elapsed is very easy. Just final time minus initial time will give you the change in time. It's very typical for batch processes. Actually, it's a transient process. So every batch process is a transient process. And the trouble or problem here is you need to feed, react, discharge, and you repeat the process. You need to repeat it because it's not continuous. So you do one cycle, and then you need to do second cycle, and then you do third cycle, and you continue until you get your desired quantity. Like if I'm producing 100 kilos of product, and my reactor can only give me, I don't know, 10 kilos per batch, I will have to do 10 times that reaction so to get 100 kilos. And this is all, of course, the time or the reaction time involved, I don't know, this is 1 hour. If I need to do 10 reactions and I need 1 hour, you will need at least 10 hours. So you will have to probably repeat. So that was about integral balances. Differential balances are the important ones. Don't get confused. So doesn't mean that integral is not important, but if I were to choose, if I were a student and I will say I don't have that much time, I will recommend you to study the differential mass balance. Unless you know your exam is about integral mass balancing or about transient processes, this will be the answer. That this, please study this. But if not, I do recommend you to study this differential mass balancing. What's up, guys? It's chemical engineering guy, and I'm going to teach you the type of processes that we're going to see in our course in mass balancing. So previously we've seen the theory in section 1. You haven't seen the video, I actually recommend to see it so you can get used to what is a process, what's a system, what's the flow, diagrams, etc. So once you see the section number 1, you could see this here, the types of process that we're going to see in mass balance. And it's in general steady state, which is typical for continuous processes. I will say this is like 80% of the course, so it is very important. Then we're going to see the transient states, which is the typical for batch, this, I don't know, 50%. And finally, we see the transient steady state combination, typical for semi-batch, only 5%. And I'm going to explain them here and give you an example of each. So here we go. Mass balance in steady states. In general, we're going to say that there is no accumulation term. Why? Because, I don't know, is for example, if we're filling a cup, water goes in and water goes out. So you're having the same height here. Or if you have a reactor, you're, I don't know, feeding 100 kilos and you're getting 100 kilos of product B, A and B. If your system will have accumulation, well, you will be like having here, and every time as time passes by, you will be filling and eventually your reactor will spill. And you probably know that in chemical engineering or chemical plants, they work like 365 days per 24 hours. And of course, many processes of those types operate at a steady state. What does that mean? That time or properties like temperature, pressure, flows, concentrations, uh, I don't know, height levels, pressure, I already told pressures, etc. Many like volume, densities, etc. Many properties will not, actually no properties will change with time. So if I come to this plant at morning, one day, one Monday, and then I go at night, one Sunday, or one Tuesday, or one Friday, I don't know, any day, or even 1 month, they should be operating the same conditions, like temperature, pressure, flows, volume, flows, etc. Of course, if they have the same production, of course, if they have, I don't know, increasing demand, they will have to increase the flow and production, etc. But if no, if you're producing the same stuff or the plant is at maximum capacity, they will stay like that no matter what the time. So that's why we have no accumulation. And this is good because we will have no differential equations, which is cool. Because differential equations, I don't know if you've seen math, but you will have something like a derivative of mass respect to time, and you have time here, and you need to differentiate, and hopefully it's easy to differentiate, because if not, you will have to use a program or a method, etc. So that's cool. Steady state's relatively easy, just arithmetics, adding, subtraction, multiplication, etc. So our mass balance equation, if you remember it, if not, go to the video before. It's about inlet minus outlet plus production minus consumption. It will yield a 0 here because the accumulation is cancelled. So what can we do mathematically? It's inlet, I will put here in, minus outlet, here out, production on the P, and consumption on the C. I have this inlet minus outlet plus production minus consumption equals 0. And I would like to let the left side the positive ones and the right one the negative ones. So everything is positive. In plus production equals out plus consumption. And let me show you examples of real life. Tell you about the chemical plants. They have reactors. They feed one mole and they take out that mole, produce it. Distillation columns, typical, they imagine this is petroleum. Petroleum is entering at 100 kilo per hour. We will, I don't know, separate 20 kilos for, because this is gas in general, like natural gas, it's propane, it's ethane, butane, etc. And we have the liquids here, which will be like gasoline, hexane, ethane, octane, all those. So they operate continually, 100 kilos per hour in general. Now we go to the mixer. You have 80 moles of A and 20 moles of B. No, it's a C. So you will be mixing, I don't know, maybe this is water and this is ethanol. You are doing I don't know, you're doing this product to sell it. Like it's alcohol or diluted alcohol for households and house use, domestic use. So let's do an example so you get more used to the mass balance and especially in the steady state here. 1000 kilograms per hour of mixture of benzene, that B will be denoting as B, and toluene, T. They actually are 50%, so it's 50-50. Are separated in a distillation column in two fractions, fraction V and fraction D. The mass flow, they tell you the mass flow rate of benzene in the top stream is 450. So I put this in my diagram. They tell me that is a data. And then that of toluene in the bottom stream is 475 kilograms of toluene. So I put it right here. The operation is steady state. Actually, they could not say that. They're just telling it to you because you're newbie and you don't know like if a distillation column is in steady state, but probabilities are that many processes that we're going to see, it's steady state. So either you suppose it or you need to know how the actual equipment works. So if they tell you a mixer is going to mix blah 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 kilos per hour, probably is in steady state. Now they tell you to write the balance on benzene and to learn to calculate the unknown components of the flow. So they want me to calculate how much toluene is in the, let's say, the fraction up in the upstream, which is V, and how much benzene is in the bottoms, which is D. Actually, it's here. So I put them letter A, the mass of toluene, and letter B, the mass in benzene in each flow. We continue. Going to see mass balance global. What's that global mean? Means that I'm going to do a mass balance in all the distillation unit. Something like this. So we need F, B, and D. We know that inlet minus outlet plus production minus consumption equals accumulation. But we know there's no production, it's only separation process, no consumption, and no accumulation. So we are left with inlet minus outlet, which mathematically, well, it's equal 0, which will be the same to say that inlet is equal to the outlet. Just because we are starting, I'm putting here the inlet, which is F, and the outlet, which is D and B. So continuing with the mass balance, you will say that the mass balance in a global, when I say global, I speak about the system, it's equal to F equal D plus B. And if we wanted to substitute, because we are told that it's 1000 kilos, so we don't want a variable, we want especially always have numbers. So we get to this equation number 1. Now, let's do a mass balance of toluene. I hope that you understand what is this. X of T means the mass composition of toluene in F. What does that mean? We are told that this is 50%, so 50% is the X. Well, we need to change 50% to 0.5. I'm hoping you know why, because if not, you need to go to math basics. You do actually don't know, I recommend strongly to understand what's a mass fraction, a mole fraction, etc. So what I'm saying here is how much of this feed is toluene. Like I know 1000 is the feed, but actually I just want to know how much of toluene is that. Thank God I have this here. I know 50% is of the feed it's toluene, so I just need to multiply 0.5 times 1000. I will have 500 kilograms of toluene per hour. That's cool. So we actually have this number. This number here, this circle, it's actually 500. Equals to 475, which is given in the data. It's given. Plus T. What's T? T actually is the toluene in V. Here is the toluene in this flow. We don't know it. I'm going to let it like T because we are actually asked to calculate T. So we let it as a fraction. No, as a equation here, sorry. Now we do the mass balance in benzene. The same here, guys. XB is the one here. If it will be, I don't know, 20, 80%, we will use 20 and 80. But this time it's only 50-50, it's the same. 50% of the feed, so 500 kilos, equals B. What's B? B is toluene, benzene in the bottoms. We don't know it, so that's why we use B as a variable. And we add 450 kilograms per hour. We have this is given. They are so cool, they give us data. Because if not, we could not answer the problem. So, what do we have here? We have three equations. We have 1, 2, 3, 4 unknowns. So, what can we do? We can actually solve. Let's try to substitute values. We already have f. We already substitute f here, f here. So number 1 will be, no, actually this is number 2. This is number 2 and this is number 3. Sorry guys. Sorry about this. Equation number 2, just you know this, I told you guys, is 500. And we have this data before and toluene. So actually we have a number, and a variable. What can we do? We just let alone the variable 500 minus 475, and that will give you 25 kilo of toluene, of course. Then the same with this equation. This is so easy. So B plus 450, we let alone B, and it's 500 minus 450, which is 50 kilograms of benzene per hour. And normally you will know that you have the whole system, you have all the variables, so you just need to go backwards and see what you are asked for. You are asked for this and this, which we already have. So that's why I'm putting him here the answers, B and toluene. That's all, everything. That was our mass balance steady state problem, exercise number 1. It's easy, not that difficult. You get to use what's that distillation column, how does it work a little bit. It is used for separation. They want to increase increase here benzene, then want to increase here toluene. Cool. Now let's go for a batch equation. A batch equation is very, very interesting. It's in general, depending on the case, if you are having a reactor, let's see this example, because we have many types of batch process. but we're going to see here the reactor one. There's no inlet. What does that mean? You feed, and once it's full, you will start the actual analysis. It's full, times 0, it's full, times 0, it's full, let's say, of A. We're going to produce this equation A turns to B with temperature. There's no outlet. I'm not going to take out with time. I'm going to wait all the A to react, and then I'm going to discharge the product. So we have no inlet, no outlet, and since it's a closed system, I'm going to have accumulation because A is dropping and B is increasing. So production, yes, we have production is actually B, and consumption, yes, we have consumption, it's A. So that's why we have accumulation, because in time 0 we will have an amount of A and B, and in time, let's say final time, we will have A and B difference. These are not the same, guys, so take care. That's why there's accumulation. The variables are changing with respect of time, so accumulation cannot be taken away. This is just one example, but let me tell you another types of batch examples. We're going to work on this exercise. It's kind of easy. It's simple. 2 methanol waters mixtures are contained in a separate flask. The first mixture contains 40% of methanol. It's here. And the second one contains 70% of methanol. If 200 grams of the first mixture is combined with 150 grams of the second one, so I have 200 in the first one, 150 in the second one, they ask you kindly what is the mass and the composition of the product. Product is the final. So what I'm going to do here is do a mass balance. Don't get used to the mass balance I showed you before, please. Like, don't get this as a law of batches. No, never do that. We need to do our analysis. Mass balance is always inlet minus outlet plus production minus consumption. So it's equal to accumulation. Accumulation could be either positive or negative. Now, there's inlets. Yes, we have 2 inlets, so it's okay. Outlets, no, we have no outlets. Production, I don't think we're producing anything. No water, no methanol is being produced. So the inlet is actually what we are accumulating, which makes sense because if I told you, if I just dropped a solution in a beaker and you ask me what's the accumulation, but of course the accumulation is the amount of stuff you just pour in. So let's continue, guys. Mathematically, the inlet is easy. M1 plus M2. Why? Inlet will give you the accumulation. And you probably don't actually have to do the mass balance to know what is the mass. Like by common sense, you could say, well, if you just pour 200 grams and you just pour 150 grams, you just need to add it. But I wanted to show you how to do it with the mass balance approach. So here it is. 200 plus 150 will give you the accumulation, which is just the addition of those 350 grams. Nice. Now, they ask you about compositions, and the only way we can check composition is doing a mass balance in a species. We could use water, but I don't like that much because we need to calculate the amounts of water. We could use the mass balance directly on the methanol. So, as I told you before, guys, I know the amount, the total amount, but I want the fraction of methanol. So it is here. Plus the amount here in the inlet, it has the same one, is inlet equal accumulation. It's M1, M2. Just be sure to check the methanol. This XX is very important. And it will give you the amount of methanol in the accumulation. Okay. If you do not understand what these X are, please go to your chemistry course and read the mass fraction section, because it's very, very important. Or you could choose to look in YouTube and look what is a mass fraction. But what I'm doing here is just simply calculating the amount of alcohol in M1, the amount of alcohol in M2, and the amount of alcohol in the accumulation, or in these 350 grams. So I just substitute data, and of course it's one equation with only one variable. The variable I'm looking for is the composition here, and I just do some maths. I get 185 divided by 350, and I get 0.529. That is almost 53% is methanol. And of course the balance, which will be 57%, is water. So we have the composition right here. We could either use water, or if we do right now a mass balance of water, we will prove so nice and so cool that 1 is equal to 1 or 0 is equal to 0. And I ask you the question, why? Just think about it. It's something about like we have 3 equations and we only have 2 variables to get, so maybe you get used to that if you do a lot of equation systems, and you know you only have 3 equations and 2 variables. You know 1 equation is not needed. And finally, guys, we're going to see the semi-batch. Semi-batch is a lot way more complex. That's why probably we only see 5% in the course. And includes continuous, which already we have, like, if not knowing like continuous and batch, like you don't understand continuous and you don't understand batch, that's why it's way much complex. But it's okay. I'm going to suppose you are masters in continuous processes and in batch processes, so you will be happy to get these more complex semi-batch problems. In general, I will say that accumulation is always included, in general, but it depends, because maybe you have like 2 sections. The first section is when you, I don't know, let's suppose you see a reactor, and you know when you start the reactor, you have this first phase where you fill it, but you don't have all the desired quantities. You don't have the conversion you want, you don't have the flow you want, the recycle you want, the product you want, because you're starting to operate that reactor. But once you start operating and you achieve the temperature, this is phase 1. You achieve the temperature, you achieve the pressure, you start getting the recycle, you start getting and achieving the product you want. You are now achieving phase 2, and phase 2 will be simply like a continuous process. Okay, I have a reactor, I turn it on. So these 2 phases is what the semi-batch is about. So as previously, you cannot know if inlet, outlet, production and consumption variables vary. So please do an analysis, please, guys. Which stuff goes in, which stuff goes out, what is the production, and of course, what is the consumption. All this will give you an equation of accumulation, and you can solve it. So I'm going to bring you an example right here. Please read I will recommend you to stop the video and read it before I read it to you guys. So I give you time. So let's read it. We're going to do an integral balance on a semi-batch process. Okay, so they already giving you what to do, integral balance. They actually shouldn't give you this. They should just tell you a semi-batch process, or not even that. They could tell you, okay, we have this process. But okay, they are so nice, they tell you do an integral balance and giving you the answer guys for everything. But don't worry. Air is being bubbled through a drum of liquid hexane. Okay, hexane is liquid. We're using air and it's being bubbled. Okay, and they give you this rate. What does this rate mean? It's how much we are feeding air. Air feed. The gas stream leaving the drum contains 10% of hexane. What does that mean? It means that it comes air here, and because we have here hexane, and the air and hexane are mixing. But you know, air cannot stay in the hexane, so the air goes out, and surprisingly, it has 10% mole of hexane, and the other one, or the balance, is air. So what it happened is, like, let's say dry air goes inside and goes out, but not only dry, it has a little bit of hexane. So it's insoluble. That's what I was talking to you, like guys, air doesn't stay inside the hexane, it just goes out. They tell you another time, use integral balance and giving you everything to estimate the time. We need to give an answer in time required to vaporize 10 cubic meters of liquid. So let's do it. First of all, I want to show you like this process here is continuous, and this process here of like the 10 cubic meter is between continuous and batch, because actually it's a batch. We are doing a batch of 10 cubic meters of hexane. So that's why it's not a continuous process, it's a semi-batch process. But anyways, let's do our mass balance, because we're used to do mass balance. Let's do it global. What does that mean? In general, in all the equipment and currents. It's equal to inlet minus outlet plus production minus consumption. Will give you accumulation. It's cool that we have no reaction, so we have no P, no C, so we only get inlets and outlets equal accumulation. Number one. Now, they don't give it to you, but you know internet exists, so you get the density. You should get 660 kilograms of hexane per cubic meter. So that's cool. We will use it later. Now let's do a mass balance of hexane. Hexane inlet, no, there's no inlet actually, so we're going to drop it. There's outlet, yes, it's going with the air, so we cannot cross it. No production because no reaction, and no consumption. So we have now this minus outlets equal accumulation. We have two equations. And finally, just to get out of doubt, let's do a mass balance in air. Inlet, yes, we have an inlet. Outlet, yes, we have an outlet. Production, no reaction, and no consumption. Accumulation, of course. No, actually, the system is not accumulating air. It's only drying hexane. Air is just going in and goes out. Sorry about that, guys. Air is not accumulated in the system. Air goes in the system and then goes out the system. So we have this equation number 3. Cool. Now let's calculate the time for the volume required. It's 10 cubic meters, so we're going to substitute 1, 2, and 3, all the data. So from 1, we have F. This one, we're going to turn it to F. And O, we're going to turn it to P, which is, I like to call feed and product. So feed is going in inside and product is going out. And it accumulates. So we have a number for equation. We can forget equation 1. And then equation 2, just O, the outlet, will be P of H. What does this mean? This means how much product of hexane, only hexane, and I will accumulate hexane. So notice, guys, that the normal accumulation of the system is not the accumulation of the hexane. And of course, it is not the accumulation of air, which is 0. As I told you before, there's no accumulation. So accumulation of air is 0. Oh, sorry, guys. Accumulation of hexane, I don't know. That's actually what we want to calculate. And accumulation of the system, we don't know it either. So, guys, now let's substitute equation 3, which will give you inlet of air equals outlet of air. We will call it number 6. We actually know the inlet of air, which is 0.1 kilomole of air per minute. Here is it, the air feed, equals to the outlet of air. You don't know the outlet of air, but you can calculate it. You know that 90% of P is air. Why? Because 0.1 is hexane, so the rest, the other amount must be air, so 0.9 is air. I do math. We have one number here, and we have one variable. We can do some math, and you get that P is 0.111 kilomole per minute. Nice. So we continue. From the density data, I told you, you can find in the internet. Don't be so childish and tell, hey, I have no density, so I cannot answer this problem. No. You are young, but yet you need to know that densities, all viscosities, all those kind of data you can find in internet so easy, you're going to use it. So let's do it. Having density, you can calculate mass with volume. You know that, guys, from chemistry classes, physics classes, common sense, etc. So the mass of hexane equals density of hexanes times volume of hexane. I just substitute this 660 kilograms of hexane per cubic meter times 10 cubic meter of hexane. You will have to get rid of 6,600 kilograms of hexane. We have the mass needed to get rid. And why are we doing this mass? And why not volume? Because we're talking about mass balance. Later on, guys, you will see that liquid is not constant. It depends, the volume of the liquid depends on the temperature, pressure. If you mix it, you have solutions that go and shrink, you have solutions that expand, etc. So never trust liquids, guys. Always trust only mass. Now, we want the moles because we're, as before I told you guys, here we're talking about moles, everything is in moles. So let's change everything to moles. You know that mass times the molecular weight will give you the actual moles or kilomoles. So mass, I told you, it's only 660 kilograms of hexane divided by 86 kilograms of kilomole of hexane. So this one goes off, and you get this amount of kilomole hexane. Good. Now from the mass balance, there will be an accumulation. Accumulation is always mass in time. As I told you, accumulation is always this little guy here. And you know mass, as I told you before, you can multiply moles times molecular weight, which is here. And you can take out this molecular weight out because it's a constant. So we have this. Let's solve it. From 7 and number 5, we know accumulation of, here it is, accumulation of hexane is equal to minus p hexane. So accumulation will be equal to this. You have two equations, now solve. You substitute this one and this one, so you get this here. And this is equal to this. Sorry for all these lines, but it's to get you know how I get this. This is very important because you now have a differential equation, which is easy to solve. You just first, we drop this one here. Molecular weight, we can leave it here, and the moles, we can leave there. So actually, we just need to substitute the amount of P. This will be the differential. Hopefully you know that's math. And you know that this here, guys, is the moles needed to take out. Why? Hopefully you know why. Because I'm not going to explain you guys. It's so easy, you need to know it. So continuing, we have, yes, we have this, and the differential will give you time final minus time initial, which is, I don't know, normally the initial time is 0, so you get the final time or the time. Just divide this guy and you get the answer in minutes, which it doesn't make that much like impression. If you say 6,000 minutes, now I will like actually know how much is. So you can change it to hours, 115 hours, or actually you can change it to days, which will be 23 times, I don't know, it's about 4 and 5 hours, 5 days to take that. So it's a long of time, a lot of time.
Okay, so we'll continue this tomorrow. Okay, napata sa kuan na, napata sa mole balance pa, no? Ang kini Thursday or Friday na to ni ma-discuss na, no? Ang kining core discussion dito, no? Okay? So, importante nga makasabot mo sa mole balance kay mo diretso ta ning ato ang kuan sa CRE nato, ato ang kuan maglisod ta og maglisod mo og basi maglisod mo og kuan no ka get sa topic especially nga online ra nga to ang kuan no paagi. Okay, please open your microphone for the uh, second attendance. Abarkis,
Present, sir.
Abasaldo,
Present, sir.
Anchita, Anchita na wagtang.
I present, sir.
Na Anchita?
Yes, sir.
Ah,
Present.
okay.
Present.
Arong,
Present, sir.
Barrios, Kevin,
Various present, sir.
Silvestre, Silvestre
Present,
Gitchell.
sir. Present, sir.
Okay, Kanyete, Hana, wa jud ni? Caballero,
Present, sir.
na-late ka?
Yes, sir.
Castañares, nawagtang Castañares. Clemente,
Present, sir.
Koyos,
Present, sir.
Dakay,
Present, sir.
Gata,
Present, sir.
Binopol.
Sanyara, sir. Present.
Present, sir. Ding lasa, sir.
Kasanyaris na
Binopol,
day.
present, sir.
Okay. Binopol na. Durham,
Present.
Scario,
Present, sir.
Brique,
Present, sir.
Brua,
Present, sir.
Gilina,
Present, sir.
Jarina, sorry.
Present, sir. Okay, sir.
Groma,
Present, sir.
Mando,
Present, sir.
Luwab. Wa si Luwab.
Present, sir.
Okay, sorry.
Sorry, sir. Lian.
Okay. Lumibaw.
Present,
Lumibaw.
sir.
Okay. Muley,
Present, sir.
Burok. Burok. Nagluto ni. Nagluto ni sudan. Nirbida,
Present, sir.
Alice,
Present, sir.
Pipito, Sabin. Pipito,
Present, sir. Present.
Iris,
Present, sir.
Brandas,
Present, sir.
Ponte,
Present, sir.
Rubin,
Present, sir.
Tanoy,
Present,
Tanoy,
sir.
Sinilio,
Present, Sir Senilio.
Susun, Susun,
Present, sir. Susan.
okay. Toledo,
Present, sir.
Vergara,
Present, sir.
Yaon.
Present, sir.
Okay, so I
Sir,
hope you
is
understand
sir.
the yes. Na si Kisay na.
Present si Morok, sir. Pero hinay lang iyang volume sa microphone, sir.
Okay, sige. Kisa pa.
Yes, sir.
Kanyete wa jud no. No, wa jenis kanyete absent man ni gani. Ha? Okay, I hope you understand the discussion of the chemical engineering guy, no? Gipili na ko tanan ng naa sa YouTube siya ray murag maayo yung pagka-discussion. Although naa siya yung mga data labi na nga sa kuan nga medyo dili consistent iyang data pagka-discuss pero makorek na nato na no. Na yung mga data siya nga dili consistent labi na sa mga percentage siguro maglibog sa siguro siya sa pag hatag no. Anyway, sa mole balance pa lang tanong wala pa gyud ta sa ato ang core discussion sa ato ang topic no. As per our to ang course guide mole balance pa ta no. It takes about 8 hours no ang pag-discuss na niya sa actually sa ato ang sa face to face dugay ko makahumog discuss ng mole balance kay if I'm going to discuss right away sa ato ang core subject or ang pinaka buod sa ato ang discussion magnganga ang estudyante no maglisod sila og sabot labi na sa online ta no kay lisod ko pagbuhatog ka ng materials dayon no ilabi na sa ato ang discussion karon nga everyday siya no lisod kay buhatan og materials dayon hopefully makabuhat na kog materials sa next sem nabuhatan na nako ni siya maayo no so sa pagkakaroon we are going to use only the mga resources na sa YouTube no mangita lang kog pinakamaayo nga kuan okay so as you can see medyo di pa kaayo siya lisod but somehow I know you understand already the mole balance between the reactors no remember reactors ang ato ang kuan ha not the vessel reactors okay guys so if you have no more questions you can log out now and God bless
Thank you, sir.
okay
Thank you,
Thank you,
sir.
sir.
Yes, sir.
Yes, sir.
sige
Sir, excuse me, sir.
yes kinsa ron Charles sige Charles
Mag-upload ba ka, sir, sa mga PPT, sir?
sa you mean to say the course guide or sa ato ang kini siya naka-record man ni siya Charles pwede nimo ni i-download no na sa atong kuan tanan natong discussion nato man ning gi-record ang activities na to will have an assignment of problem solving, no? Ang ato ang schedule sa atong quizzes every Monday, no? Then assignment nato between, no, mangita lang tag time nga available, no? Basta nasa weekdays ang ato ang kuha na to assignment, no? Ito mga problem solving before ta maghato problem solving. Doon na tayo ka ng assignment. For example, mall balance siguro mag-assignment siguro ta gamay ana kay di pa magka-share ka ng nga na komplikado, and you are going to solve it, no? Saturday and Sundays, and then you can submit it by Monday or Tuesday. Yung lang. Okay?
Ay, sir. Na ini kuan sir na di daw sila ka-download sir kay hinay daw ila net sir.
Di na ilang need.
Mm.
Ako lang i-download niya, i-try na kong butang sa kuan sa Moodle, no? Para makita niyo dito. Okay? Sa Moodle na lang ko ibutang. Ha?
Okay, sir.